So, remember we talked about the four Fulkerson algorithm to find the maximum flow in a capacitated network. And what we did not prove really is that when the algorithm terminates, then we indeed have a maximum flow. Okay, so that still needs to be proved. So let's just recall when does this algorithm stop? Okay, when do we? Okay, this is the flow that I'm going to return out of this algorithm. Well, the stopping condition is very simple. So stopping condition is the following: that if the current flow and residual graph here there does not exist any positive. Okay, so that's our stopping condition. If on any iteration we find that this is happening, then we just end the algorithm there. Now, what's the guarantee that if this happens, then F is really the maximum flow in this network? Okay, that's what we are going to prove today. Okay, so the way we are going to prove is the following. We would be using the notion of an ST cut, which we had also introduced last time. So I hope everyone remembers what an ST cut is. Well, it's simply a partition of the set of vertices into, let's say, two disjoint sets A and B, such that S belongs to A and T belongs to B. So that is a requirement. So कोई भी partition ऐसा अगर होता है, तो then we will say that this is an ST cut. Yeah. And what is the capacity of an ST cut? Well, the capacity of a cut is the sum of the capacities of edges that are going from the A side to the B side. Yeah. Note that we are not using any other edges while counting the capacity of a cut. Good. So that is what. So in order to do this proof, we have to go through via the notion of an ST cut, and you will see how. Formally, I'm going to do the following. I'm going to prove the following theorem. Is given a flow F in G, the following statements are equivalent. Okay, so I will write three statements. What I'm saying here is that if I'm given a flow in my network, then all the three statements that I'm going to write, they are equivalent. Okay, and that will give a proof that this algorithm is correct. It really gives you the maximum flow. So the statements are the following. Maximum flow. There exists ST cut such that the capacity of this cut is equal to the value of the flow. Okay, that's the second statement. The first statement is it does not exist and positive capacity Okay. Oh, there's an issue with my voice. Okay, let me see what I can do about this. Sorry, I didn't see this message. Is it better now? Is it somewhat better? Okay, thank you. Sorry, I did not see this message. Okay, so yeah, since my voice was not clear, let me just repeat what I'm trying to say. So in order to prove the correctness of Fulkerson, I'm going to prove the following theorem. So let's say I'm given a flow in my graph, any flow in my graph, and I'm going to prove that these following three statements are equivalent. Okay, there are two B's here. So let me make this C. So the following statements are equivalent. Yeah. And what are they saying? That F is a maximum flow. This is equivalent to saying that there exists a cut in the graph. Okay. I'm not saying this for every cut in the graph. There exists a cut AB in the graph, which is an ST cut, such that the capacity of this cut is equal to the value of the flow. Yeah. And the third statement says that if I construct the residual graph of this flow, yeah, then in this graph, there is no ST path which has a positive capacity. Okay. So I'm going to prove that these three statements are equivalent. And you can see that this immediately tells us that the fourth, if I'm able to prove this theorem, then it immediately gives me that the Ford-Fulkerson algorithm is correct. Why? Because, well, it's, if C and A are equivalent, then means that not finding an ST path in your residual graph is really an optimality condition. It really tells you that F is a maximum flow. And C is really, so the statement C is really the stopping condition of Ford-Fulkerson. Okay. So once I have this theorem, I am done, is what I'm claiming. So let's try to prove this. So I don't know if you have seen proofs like this, maybe in your discrete maths class or something like that. So the way we prove that three statements are equivalent is we go in a cyclic fashion. Okay. So here is what we are going to do. We are first going to prove that B implies A. Okay. So proof. So we are first going to prove that B implies A. Next, we are going to prove that A implies C. And finally, we are going to prove that C implies A. Okay, so we are going to go, C implies B. So we are going to go in a cyclic fashion. We'll prove B implies A implies C, and C implies B. That proves that these are all equivalent. Okay, so this is how you prove that a bunch of statements are equivalent. Yeah, this is a generalization of the if and only if kind of thing. Any questions so far? Okay, is the statement of the theorem clear to everyone? Okay. So let's try to prove that B implies A. Okay. Now here is what I claim. So claim is, so I'm claiming a more general statement, and we will see that this claim will prove that B implies A. Okay. So the claim I'm trying to make is the following: given any flow, okay, let me see. Given any, yeah, this is fine. Given any flow F prime and any cut AB, the capacity of the cut is at least the value of F prime. Okay. So I'm trying to prove a somewhat more general statement than what I'm trying to prove here. So I try to prove that B implies A. But what I'm proving is that you give me any flow and any cut in the graph. Okay, I don't care which flow you are giving me or which cut you are giving me. I can always prove that the capacity of this cut is an upper bound on the value of the flow. Okay, so let's see why this immediately gives us B implies A. So I'm saying that if I'm able to prove this claim, then I essentially prove that B will imply A. Why is that? Okay. So in order to see this, so suppose we have proved the claim. Suppose we have this claim. Okay. Now let's try to sort of so I will give you sort of a cartoon proof of this of why this implies B implies A. So suppose I try to plot. So suppose this is the real line. Okay. So suppose I have 0 here, and this is plus infinity or something. Yeah. So I'm just showing the real number line. Yeah. And let us plot all the possible values of the cuts, all the possible values of the capacity of the cuts in my graph. Remember, these are all ST cuts, right? And all possible value of the ST flow in my graph. Okay. So if I'm able to prove the first claim, okay, the one which I've written above, this one, okay, then who can tell me how should this figure look like? So if I try to, let's say I use crosses to denote the capacities of cuts, and circles to denote the capacity of the flows, or the value of the flows on this real number line, then how should the crosses and the circles be placed on this line if I'm able to prove this claim? Let's say I have proved this claim. So the question is, how should the crosses and the circles be distributed? Let's say the crosses denote the cut capacities. Yeah. And let's say the circles denote the value of flows. Okay. So my question now is, how should the crosses and the circles look like if I project them on this real line? Yeah. Okay. So yeah. So the answer is that what I've proved here is that the value of any flow is upper bounded by the value of any cut in my graph. Okay. Suppose I have proved this. So then this clearly means that all the circles will be on the left of all the crosses. Right? This is what the claim is saying essentially, that if you look at the value of any cut capacity, then that has to be either greater than or equal to the value of any flow. So all the flow values will be all the flow values would be kind of to the left of the leftmost cross, as Atisha has said. Okay, is this clear to everyone? This is a pictorial representation of the claim that I have written above. Okay, now if this is true, now let's see what the statement B tells us. The statement B now tells us of a special condition. Okay, what it says is that suppose there exists, suppose I'm given this flow, and suppose there exists a cut AB in my graph such that the cut capacity and the flow value are exactly equal. Okay. So how does that look like if I try to draw this in my cartoon? So this essentially looks like the following, that there exists some cut, so there exists some cross and some circle which are juxtaposed on each other. Okay. This is what the statement B is saying, that suppose this happens. Okay. So if this happens, what can I say about this particular circle on which this cross is juxtaposed? Is this something special with respect to flow values? Okay. So I claim now that if this condition happens, then the flow value that is given by this circle is actually the maximum flow in my graph. And I think that's immediately clear from the picture. Why is this the maximum flow? So suppose this is not the maximum flow. Okay. But if this is not the maximum flow, then what has to happen in this picture? Well, then there has to be a flow value which is to the right of this to this box. Yeah. But if it's to the right of this box, it means that there is a cross which is to the left of a circle. And this cannot happen. Okay. That means that this blue thing, this is really the maximum possible value of the flow in my network. Okay. So this is a contradiction. This red circle cannot exist in my picture. Okay. So claim 1, claim implies if B is true, then F is the maximum flow. Okay. Any questions about this? Of course, I have to still prove this claim. I have not shown you the proof of this claim that I have written here, which helped me draw this cartoon. But if I have this claim, then I'm done essentially. So is there any question about that part? Okay. If there isn't, then let's try to prove the statement, the claim that I have written here. Yeah, that the capacity of any cut is at least the value of any flow. Okay. So remember, we said that we denote an ST cut in an abstract way, right? And this is the way we denote an ST cut. So suppose this is your cut. So this is the A side and this is the B side. So remember, you have to have S on the left and T on the right. Okay. Now, what kind of edges what kind of edges can I show on this picture? Well, there are 4 kinds of edges. Yeah. So there are edges, let's say I denote them by green, which are going across from A to B. Yes. There could be edges that are sticking into A, like that. And there could be edges which are completely inside A. And there could be edges which are completely inside B. Okay. So these are the 4 kinds of edges in my graph. If I look at it from the point of view of this cut. Okay. And remember, when I am talking about the capacity of the cut, I am only taking the green edges into consideration. Yeah. I'm not taking any of the blue, purple, or red edges. Yeah. So the green edges really define the capacity of this cut. Okay. Okay. So now let's say we are given some flow. So what is the value of the flow? Well, the value of some flow f prime, by definition, I know that this is equal to summation of f prime of E, where E belongs to delta plus of S. Yeah. So yeah, if you really want to see a picture, then let's say this is delta plus of S. Yeah, all the edges that are going out of S. And I have assumed that there are no incoming edges to S. Remember, this is an assumption that I had made in the first lecture of flow, that there are no incoming edges to S. So this is the value of the flow. Given f prime, given a flow assignment to your edges, this is what we denote as the value. Okay. Everyone with me on this? Good. So now I'm going to claim that this is equal to a more interesting quantity. I'm going to claim that this is equal to summation of E belongs to delta plus S, f prime of E, plus summation over all vertices that belongs to A but not S. Okay. Summation of E belongs to delta plus of V, f prime E, minus summation of E belongs to delta minus of V, f prime of E. Okay. So why do you think I can write this? why is this one equal to this one? So it seems like I have added a lot of quantities to what I started with. But why could I write an equality here? So which property of the flow f prime helped me write this statement? Okay. So what am I really doing here? I'm looking at all the vertices that are inside A. Yeah, remember AB is a partition of my vertex set. So there would be a lot of vertices which are part of A. I'm just taking all those vertices and I'm writing this thing for every vertex in A except S. Yeah, S I have left out. So I started with the value of f prime. I know that the value of f prime is this quantity, but then suddenly I am claiming that this is equal to this quantity. Very good. So I have an answer, which is the correct answer. So I'm just writing the flow conservation constraint for all the vertices in A except S. Yeah. So this just follows from the flow conservation constraint. I know that the total flow into a vertex is equal to the total flow that is going out of this vertex. And I'm just writing these, essentially I'm writing this difference for every vertex. So this contributes 0 to whatever I have here. Yeah. So everything here essentially adds to 0. Okay. Everyone with me on this? Yeah. Okay. Good. So now what I will do is I will write this summation in a slightly different way, but I will write it from an edge-centric point of view. So remember this, whatever I've written so far is a more vertex-centric view of the value of the flow. Now I will try to express this flow as the summation of flow on the edges. Yeah, instead of writing the vertices or taking the summation on them, I will just take a more edge-centric point of view. Okay, so let's see. Okay. So let's think about this. Okay. Um, let's take an edge which is of the blue nature. Okay, first let's take the easy thing. Let's take an edge which is red. Okay, let's take a red edge. Okay. Uh, so this red edge has some flow on this, right? Does this flow affect this summation at all? So the question is, does the flow on the red edge appear in this summation either with a plus sign or a minus sign? Well, the answer is clearly no, because I am only writing this for the vertices which are inside A. Yeah, so there is no way that this red edge will appear in this summation. So the red edges I can forget about. I don't have to write anything about them. Okay. Now let's talk about the blue edges. Okay. So in this summation, how many times does this edge appear, and with what signs? So how does a flow on a blue edge behave in this summation is what I'm asking. Do they contribute anything at all? Very good. Okay, so the answer is it appears twice, once with a plus sign and another time with a minus sign. And why is that? Well, it clearly appears with a plus sign when suppose you write for this vertex. Okay, when you write this conservation kind of thing for this vertex. But remember, it also appears with a minus sign when you write the conservation constraint for this vertex. Okay, so the blue kind of edges, their flow, it contributes a plus f of e once and a minus f of e once. So in effect, they cancel each other out. Okay, they essentially cancel each other out. So then who can tell me what am I really left with? So after discarding the red edges and the blue edges, what am I really left with if I write this summation? So in terms of the edges, So which are the edges really that appear with a positive sign in this summation and which do not cancel out? Which edges are relevant for that? So I hope everyone gets the question, right? So what I'm asking is that, there would be these cancellations and all that. So which are the edges that whose flow, stays back in the summation after I have done these cancellations? Which are the only edges that are relevant? Yeah, so green and purple are the only relevant edges whose flow matters in this summation. So whose flow appears with a positive sign and whose flow appears with a negative sign is what we have to figure out. So I think the answer is pretty clear. So for E, which are in delta plus of A, they will all appear with a positive sign. Yes. And the edges which are sticking into A, so the purple edges, they will appear with a negative sign. Okay. Any questions about this thing? Very simple. So I just broke this summation down. I took an edge centric point of view. I figured out that the blue edges, uska flow, they appear twice, once with a plus and another time with a minus. So they cancel each other out. The red edges don't matter to me. I'm not even writing their flow in this summation. So the only edges that are remaining are the green edges, but their flow comes with a positive sign, and the purple edges whose flow come with a negative sign. Yeah, good. Now, what is an upper bound on the first term on this summation? Okay, so if I look at this first term, can I say something? Can I say that this is upper bounded by some quantity in this picture? At most something. So this could be at most something. Can I say something like that? Okay. So one answer is sum of edges out of S. Yeah, so it should not just be S, right? I think you want to say it's sum of edges out of A, right? Okay, so all you need to say here is that jo bhi flow the green edges par hai, they are upper bounded by the total capacity of the green edges. Yes, so jo bhi hamara total capacity hai on the green edges, that's an upper bound on the first quantity. Yeah, and this comes from the capacity constraints. Remember, f prime is a valid flow, so the capacity constraints must be satisfied. Okay, so this is, so now I can say at most, this is the capacity of A comma B. Yeah, and why? Because this is sum of capacities of green edges. Yes, but I have this annoying minus sign. Okay, so remember, if I have to prove that what I need is just this thing, remember that's what I am trying to prove, that the yeah, so let me come to that. Yeah, so remember I only need this thing, but there is a negative thing here, but we will take care of that. Okay, so there is one request. Could you explain once again the third equality? So do you mean how we reached here from here? Okay, so here is what we are trying to say. So let's look at these quantities, right? Yeah, and now let's take an edge centric point of view. So think of a blue edge. Okay, so the flow on the blue edge, how many times does it appear in this summation? So I claim that the flow on the blue edge, it appears once with a plus and another time with a minus. Yeah, because you would be writing the FE values for some vertex for which the blue thing is an outgoing edge, and then for another vertex for which the blue edge is an incoming edge. But both these are part of A. So both the endpoints are part of A. So you will be writing this thing for both of them, right? So whatever the flow on the blue thing is will appear twice, once with a plus, another time with a minus. So they cancel each other out in this summation. Yeah. If I think of the red edges, they don't matter to me because I'm not even writing these summation for the endpoints of the red vertices because they are entirely in entirely in B. Yeah. So the only thing that now I have to worry about are the green edges and the purple edges. Yeah. So let's think about a green edge. Yes. So when does the flow on the green edge appear in this summation? Well, it will appear. So suppose I take this green edge, then iska flow will only appear when I write this summation for this vertex. Yeah. Okay. But remember, this edge, the green edge ka jo flow hai, that will never appear with a negative sign in this summation. Why? Because it would appear with a negative sign only if I consider this vertex in the picture. But this vertex I'm not considering. Okay. So the flow on the green edge, it only appears with a plus sign in this summation. It does not appear with a minus sign. And by the same logic, whatever edge is sticking into A, that flow will only appear with a minus sign in this summation. That will not appear with a plus sign. Because wo plus kiske liye hoga, it will happen for this endpoint. But this endpoint is not in my summation. I'm only writing this for vertices inside A. Okay. Yeah. Good. So good. So I'm still a bit annoyed by this last term, right? I don't want this negative term in my claim. Remember, what I'm trying to claim is that the value of the flow that I started with, this is at most the capacity of AB. Yeah. But I have this annoying negative term. But does it really bother me? Can I get rid of this completely? So the question is, can I remove this when I give a less than or equal to? Can I remove this term or not? We can remove it as sum of capacity is always positive. No, this is just a flow, right? Oh, sorry. So there's no capacity here. Remember, there's a minus sign. I cannot replace this with the capacity. Then I cannot have less than or equal to, because this part is at most the capacity of these edges. But if I have a minus sign, then I cannot replace this with capacity. But do I need to go to capacity? What can I say about these flows? So there is always a third property of flow which we tend to forget, which is very important. So what is the third constraint? One is capacity and one is conservation. Exactly. So this quantity is always greater than equals to 0. Okay, by non-negativity of flow. Remember, flow is always non-negative. If it's a valid flow, then it has to be non-negative. And if this term is non-negative, then I can just remove this thing. Okay, it doesn't matter to me. So I can always remove a non-negative quantity and upper bound the rest. Okay, questions? So that proves our claim. Yeah, and the claim, as we said, proves that B implies A. Any questions about this? Okay, so this implies, so this plus the cartoon implies B implies A. Okay, there's a question. What do you mean when you said that we can't subtract a capacity? So the point is, if you want to use capacity here, right? So suppose you want to, just like we did for the first term, you want to replace this thing by the capacity of these edges. Yeah, but I know that Fe is at most the capacity of this edge, right? But there is a minus sign here. So if Fe is, so let's say if Fe prime is less than or equal to Ce prime, then this implies that minus of Fe prime is at least minus of Ce prime. Okay, but then your inequality is in the wrong direction. You want a less than or equal to, but if you have a minus sign, it will change its direction, right? So an upper bound here does not help. This is all I said. But we are not using that. We are just using the fact that Fe primes are all non-negative. Yeah. So this entire thing is non-negative, is the only thing that I'm using. Yeah, good. That's a good clarifying question. Any other clarifying question? Okay, good. So now we want to prove that A implies C. Okay. So let's recall what A is and what C is. Yeah. So A says that F is a maximum flow, and C says that there does not exist an ST path of positive capacity in GF. And I want to say that A implies C. So if I were to tell you that F is really the maximum flow in the graph, then I want to say that there does not exist an ST path of positive capacity in GF. Remember, I'm not claiming the reverse yet. In fact, that is something what we are trying to prove in the theorem. All I'm saying is A implies C. If F is a maximum flow, then there cannot be such a path. So who can tell me why is this true? Or how should we prove this statement? Okay, so in shorthand, this is what we are trying to prove. F is max flow implies no ST path in GF with positive cap. So who can tell me why is this true? Or how should we prove this? It's a one sentence that you need to write really. Excellent. Okay, so yeah, I've got a couple of answers and both of them are correct. So the way we prove this thing is by a technique which we called contrapositive. Okay, you can think about it as contradiction if you want. So, but contrapositive is the more official term for this technique of proof. So so essentially I will prove the negative of the other direction. Okay. So suppose that there exists an ST path. Okay. So what does contrapositive mean? That if I have to prove, suppose I have to prove A belongs to B, this is equivalent to proving that not B implies not of A. Yeah, this is what I mean by contrapositive. So this is the technique that I'm going to use. So what is not B here? Not B means that this part of the statement is not true. So there does not exist an ST path is not true, which means there exists an ST path in GF with positive capacity. Okay. But if there exists such a path, then I can always improve the value of my flow. But if I can improve upon the value of my flow, then F cannot be a max flow. So that means this is not of A. Okay. So this is simply what I'm saying. Suppose there exists ST path in GF, then this implies we can increment on F, which implies F is not max flow. Okay, that's it. So if A is true, then C has to be true. Please remember this does not mean C implies A. Okay, that is much more non-trivial. That is what we are going to prove eventually. Okay, any questions about this thing? Okay, so we are two-third way down the line. So we have proved that B implies A. We have proved A implies C. The only thing that is remaining now is C implies B. Okay. So let's recall what C is again. So C says that given this flow, there does not exist ST path in GF with positive cap. Okay, and this, remember, I'm given this flow, right? What I have to prove is the following, that if such a thing happens, then I can demonstrate a cut, right? So what is the statement B? It says that there exists a cut, there exists an ST cut in G such that the capacity of this cut is exactly equal to the value of the flow. So the way we are going to prove this is the following. If the statement C is correct, then I'm going to exhibit to you such a cut. Yeah. Okay, everyone with me? So all I'm going to do is I'm going to assume that C is true, and I'm going to exhibit to you an ST cut such that this condition is satisfied. Okay, this is all I'm going to do here. Okay, so remember, I have to demonstrate to you a cut now, right? So here is how I construct this cut. So construction of the cut. AB. Okay. Remember, all this is thought experiment. So this is not part of our algorithm or anything like that. So when I say construction, I mean I construct this for purpose of the proof, not as a part of the algorithm. Although you will see that this indeed gives us an algorithm to find something interesting, but that comes later. Okay. Now I'm just doing a thought experiment. Okay, so let's look at now the residual graph. Okay, and please, get into kind of a habit of keeping these two graphs in mind. So one is the real graph, which we have, but here now I'm showing you the residual graph. Okay. Now suppose I have S here. Okay. I start a BFS from S. Yeah, all this is thought experiment. So I start a BFS on S, and I'm only taking the edges that have positive capacity. So when I run my BFS, I'm discarding the edges that have zero capacity, yeah, in the residual graph, right? So I know that I would be possibly reaching some vertices. I don't know which vertices I'm reaching, but surely I vertex in my graph, some vertices. In the worst case, maybe I don't reach any other vertex, but that's fine. Then maybe S is the only vertex that is reachable from S in the residual graph. Okay, but in general, the picture can look like this. So maybe you have reached this vertex when you started your BFS from S. Okay. So now I declared this to be a cut, right? So formally A equal to set of vertices reachable from S in G of F. Please remember, the G of F is very important here. Okay, I'm not doing this on the original graph that is given to me. I'm doing this on the G of F. Now, by the condition C, what can I say? So what does condition C give me about this set A? So if condition C has to be true, then what cannot happen in this picture? Okay, more specifically, which vertex should not appear in A? Excellent. So T cannot be part of A, clearly, right? Because that's the condition that we started with. So T has to be on the other side. Yes, and there might be other vertices. I don't know. But what is surely true is that T is not in A. Because if T is in A, then your condition C is not true. That means that you have a path from S to T in the residual graph. So now I can safely say that A and let's let v equal to v minus a. So AB is an ST cut. Okay, this is some ST cut. अब मुझे पता नहीं ये ST cut से कुछ फायदा होगा कि नहीं, but at least this is some ST cut that I have constructed. ठीक है, great. Okay, now who can tell me? So suppose I am disregarding the edges with capacity 0 or with residual capacity 0 in this GF. Okay. Now, if I look at this boundary, if I look at this threshold of A and B, so remember in the previous picture, I had this 4 kinds of edges. Yeah. So who can tell me which edges can appear in this picture and which edges cannot? So can all the 4 type of edges now happen if I take this particular cut, or is there some category of edge that does not occur? So let me show you the edges that can happen. Okay, that what are the possibilities? So one possibility was this thing, another possibility was this thing, a third possibility was the blue edges, right? And the fourth possibility were the red edges. Okay, so some people are claiming that the green edges cannot appear in this picture. Why is that true? So they are claiming that, okay, the blue can appear, the red appear, the purple can also appear, but the green edges cannot appear. Okay, so the reason for that is very simple. So let's see, how did we construct this cut? Well, I reached all the vertices that I could, starting with S, right? Now, if a green edge like this appears in this cut, then what does this mean? This means that this head of the green edge, that is also a vertex that is reachable from S. So then I should not have stopped my BFS procedure at this point. Then my BFS procedure would have continued, and it would have included the head of this edge in the set A. बट ऐसा तो हुआ नहीं है, उसका मतलब ये ग्रीन एज एग्जिस्ट ही नहीं करता है. सो इन द रेसिडुअल ग्राफ दिस ग्रीन एजेस कैनॉट एग्जिस्ट. ठीक है, सो इसको मिटा देते हैं. दिस कैनॉट एग्जिस्ट, एवरीथिंग एल्स कैन एग्जिस्ट. सो द पर्पल एजेस कैन एग्जिस्ट इन फैक्ट. Everyone with me? Remember, I'm showing this on GF. Okay. But now the point is, remember, I have to, so if I have to give you the condition B, then I have to argue something in the original graph. I have to exhibit the capacity of my cut in the original graph, and I have to prove that this capacity ka jo value hai, the capacity jo hai, that is equal to the value of this flow, right? So let's redraw the picture, but now I am showing you the original graph. So this is G. However, I'm still looking at the same cut in my graph. So this is A. This is the same A from the picture above. So I have S here and I have T here. Okay. Now what we figured out is that these edges can only appear in GF. But in this original graph, of course, I have all the other edges. So I have both the green edges and I also have some purple edges. Okay. Okay, everyone with me? Any questions, any doubts about what I'm showing? So now I am switching back to the original graph, but I'm sort of looking at the same cut that I have constructed in the residual graph. Okay, now who can tell me, if I look at the flow F in this graph, yes, what can I say about the green edges? What is the speciality of the green edges in the second picture with respect to the flow F? Excellent. Okay, so one answer, yeah. So one answer which I have is that if I look at the green edges, so suppose let's give it some name. So let's say this is the edge E prime. Then what she is claiming is that f of E prime is equal to the capacity of E prime. Why is this necessarily true? So suppose not. Suppose this is not true. Okay, but this is a flow, which means that the flow is at most C prime. But let's say there is a residual flow. Okay, but remember this is a forward edge, right? This is an edge in my graph, which means that there is a forward edge like this with residual flow left. So what does this imply for the residual graph GF? Well, this simply implies that this edge also appears in the residual graph. Yes. So if there is a residual capacity left on this edge, remember this is a forward edge. So this implies that in the residual graph, this dotted green edge, the copy of, essentially this edge also exists in this graph. Okay. But we know that cannot happen. The only edges that exist in the residual graph across this cut are the purple edges, which are sticking back into A, which are not going from A to B. So this means that all the green edges in the second picture, so this cannot happen. So all the green edges in this graph, they would be saturated. There cannot be any residual capacity left on these edges. Good. Now let's see. What can I say about an edge, let's say E double prime? What can I say about this edge with respect to the flow F? Okay, so I claim that f of E prime, E double prime is equal to 0. Why is this true? So surely this cannot be negative because we have proved that Fulkerson always maintains a valid flow. So if this is not 0, then this is positive. तो ये पर्पल जो एज है इस पे अगर पॉजिटिव फ्लो है व्हाट रिपरकशन डज इट हैव इन द रेसिडुअल ग्राफ व्हाट काइंड ऑफ एज वी विल हैव अगर ये एज पे पॉजिटिव फ्लो है right. Okay, so now let's remember how we constructed the residual graph. So agar remember in G this is a forward edge, right? I'm showing this graph G and this purple edge is a forward edge in G. तो अगर फॉरवर्ड डायरेक्शन में कुछ पॉजिटिव फ्लो है तो बैकवर्ड एज जब हम लगाएंगे इन GF, what is the capacity then? Well, the capacity is equal to the flow that I have here, but then again means that in the residual graph I will have an edge like that which will have a capacity which is positive. If Fe double prime is positive, then the capacity of this dotted green edge, which does not exist, but if वो exist करता तो इसका positive capacity होता, which again is a contradiction. Yeah, because I know that this green dotted edges cannot exist in my residual graph. So this fact gives me now to summarize, what did we achieve? What we achieved is if I look at my original graph, then the green edges would be saturated. The edges that are going from A to B are saturated, and the purple edges which are sticking back from B to A, they will have a flow of 0. They cannot have any flow on them. Okay? So these are the two properties that I have. अब अगर ये true है, तो what will happen now? So now let's go back to this bunch of equations that we had written. Okay. So what we wrote here is that the value of any flow, we arrived at this kind of a situation, right? So we started with the value of the flow and we arrived here. So let's just rewrite it in the context of the current flow. So the value of the flow F is equal to summation of f of e such that e belongs to delta plus of a minus summation of f of e where e belongs to delta minus of a. Okay? Good. But now I have a special kind of a and b. This is not just any a and b. This is an a and b that I have constructed out of some condition. And I have proved all these very interesting properties about this cut AB, right? So what can I replace the first term with? Well, now I can just say an equal to. Okay. So I have proved that for all the green edges, so the edges which are of this category, the flow is exactly equal to the capacity of the edges. They are completely saturated. So if they're completely saturated, then I can simply say this part is equal to this part. Okay. So this is capacity of E where E belongs to delta plus of A. Okay. Minus, what can I say about this part? Well, I have just proved that this part is 0. Yeah, because all these, the edges that are considered here are all the edges that are sticking into A. These are all the purple edges, but I have just proved that the flow on these edges is 0. Okay, so now I don't even need the less than equal to, but I can do a stronger claim, which is exactly equal to. So this is this minus 0. Okay, but by definition, this is exactly the capacity of this cut. Okay. So the total capacity of the green edges by definition is the capacity of the cut A comma B. Any questions? Doubts? Yeah. Okay. So this essentially proves that. So this proves what? This proves that C implies B. Right. So what we have ended up. So to summarize. What we have proved is B implies A implies C, and finally we proved C implies B. Yeah, and that gives us the theorem. Right? So in particular, now it gives us two things. So the corollaries are the following. So or consequences, corollaries. So one, Fulkerson outputs a maximum flow upon termination. Okay. And the second thing which we have is that the maximum flow is equal to the minimum capacity cut. Okay. Yeah, so these are easy consequences. The first thing, well, this is true because this is essentially what we proved when we said C implies B. Yeah, remember C is the stopping condition of Fulkerson, but we just proved that this stopping condition is equivalent to saying that F is really the maximum flow in this graph. Okay, so that proves the correctness of Fulkerson. And the second property is essentially a consequence of B implies A or whatever, A implies B. Yeah, remember if we look at this cartoon, then if I have a condition that the cross and the circle, they meet each other at some point. Yeah, so if this meets at some point, then what we can claim is that this is the best value of the circle, and this is also the best value of the cross in some sense. Yeah, or rather this is the maximum value of the circle and this is the minimum value of the crosses. Yeah, so the crosses cannot go on this side, and the circles cannot go on this side, which means that the minimum capacity of any ST cut is equal to the value of the maximum flow in the graph. Yeah, so this gives you the classical max flow equals to min cut theorem. Any questions about this? All right. So let's talk a bit about, so now that we have proved the correctness of Fulkerson, let's talk a bit about the running time of this procedure. Okay. So what is the runtime of Fulkerson? Is the question, right? So let's think about, okay, so let's actually open up the notes from last time, because I have the Fulkerson right. So this is my Fulkerson algorithm. Yeah. So who can tell me now what is the runtime? Okay, so first let's do one step at a time. So first let's figure out what is the runtime of the inside of this loop. So remember, I'm repeating this process of finding ST paths in the residual graph. Okay, so the question I'm asking is, what is the runtime of this part? Well, the answer here is that what are you doing here? Right. So you are doing a BFS, yeah, which will take, let's say, order n plus m time. And suppose so I'm assuming that every vertex is reachable from S. Okay. If I assume that, I can simplify this as order the number of edges. So this part takes something like theta of, let's say, mod of E. Yeah. Why? Because, okay, there is a small thing here. You are blowing up the graph. Remember, you are running this procedure on the residual graph. The residual graph has more edges, but it's only double the number of edges in the original graph. So the BFS or DFS or whatever path finding algorithm you want, that will take like order like theta of mod E time to run this procedure. And then you are essentially, there is something else that you need to do here, but this just takes another theta of E time. You are going over every edge along this path and you are changing the flow. So potentially this can take like theta E time. So in a nutshell, this entire inner thing that takes like theta of mod E. But the question is, how long does this procedure go on? That is not very clear. I have written here repeat, and remember the stopping condition is that we have so there is no ST path from there is no ST path in the residual graph. Okay, the question is how long this procedure lasts. Okay, so there is a request for a clarification in C implies B. So let me come to that after I finish this, right? Okay, so I will come back to that clarification. Yeah. Okay, so yeah, who can tell me how long does this procedure last? So this repeat loop, can this go on for a really, really long time, or is there a bound that we can give for that? And if so, then how? Okay, yeah, that's yes. So that's a smart answer. Well, what cannot be bigger than sum out of S? Exactly. Yeah. So all these are valid. Bounds. So there are two answers. I think 3 people have answered, and there are 2 answers essentially which I have. So one answer is that, let's say F star is the value of your max flow. Yeah. So suppose F star is max flow equal to value of max flow. Okay. Remember, we had proved that the value of the flow increases at every iteration. Okay. By the way, I forgot to mention something. So these paths along which we increment the flow, they have a special name. So they are known as augmenting paths. Okay. Yeah, I somehow forgot to mention this term. This is a very important term in the flow literature. So these paths, these ST paths that we are finding at every iteration, they are known as augmenting paths. Yeah, and the reason they are known as augmenting path is because you are augmenting the flow in some sense at every iteration using these paths. You are increasing the value of your flow. Okay. Now remember, we argued that the flow value strictly increases it strictly increases at every iteration. Yeah. So it starts with 0. Yeah. Remember, the initial flow is 0, but it strictly increases at every iteration. However, it does not only increase. There is something else that we have to argue here. If we have to bound the number of iteration, then we have to say something more about the amount of this increase. So what can I mean, which property do I require here from my input so that I can really bound the number of iterations? Yeah. So remember, we assumed here that all the capacities are integers. So if all the capacities are integers, then yeah, so non-negativity does not work. Remember, because if the capacities are real numbers, then I cannot claim that then maybe your flow increases by a very, very tiny amount in each iteration. And as I said, if the capacities are real numbers, then one can prove that this process is not going to terminate. Okay, so this has to do with how you represent real numbers on a computer and all that. But assuming that everything is an integer, yeah, all the capacities are integer, I know that if the flow has to increase, it has to increase by an amount of at least 1. Yeah, because how am I increasing the flow? Well, I'm picking this delta, and this delta is essentially the capacity of some edge. But if it's the capacity of some edge, then it's an integer. So the flow always increases by some integer, and some integer ka minimum kya hai? It's 1. If I start with 0 and I increase the flow by at least 1 in every iteration, तो ये कब तक चल सकता है? Well, वो तब तक चल सकता है जब तक मैंने max flow reach नहीं किया. So if f star is the value of the max flow, then clearly the total number of iterations is f star. ठीक है? So now let's go back to the new thing. Yeah. So this is theta mod of E for PFS DFS, and let's say theta, okay, order f star iterations where f star is the max flow. This implies order okay. So that's the yeah. And now, as someone said, that you can also say that this is the at most the capacity of, let's say, delta plus of s. Yeah, so you can also use that as an upper bound, क्योंकि s से जो भी capacity है, but you know this might be an overestimate. Yeah, why? Because remember, f star is upper bounded by the mean cut in my graph, but s, the singleton s is not necessarily the mean cut. तो हो सकता है ये जो capacity of delta plus s, that is huge, but your real max flow is much smaller. So in that sense, f star is a better bound. Okay, it's a tighter bound in some sense. In the worst case, of course, these two could be equal. Okay. Now the question is this a good running time? Is this a satisfactory running time? Are we satisfied with this kind of running time? No. See, okay. So question is, I need to know max flow. See, you are not knowing anything here. We are just estimating the running time. No. We are not. I mean, we are estimating the running time. See, you are running your algorithm. All we are saying here is that the total number of iterations would be equal to the max flow, whatever that is. Okay. How are we? Estimation of the runtime should be, yeah. So you can say that it's equal to the mean cut. Mean cut is a property of the input, right? So think about f star as the mean cut instead of the max flow. So mean cut has nothing to do with the flow as such, right? Yeah. Aditya, did you get what I say? So you don't have to know f star. You can just compute the mean cut in your graph, and that will give you. Okay. Right. Okay. So where was I? Okay. There's another question. How are we taking theta a in the BFS? चलो theta a नहीं है, order ही है. ठीक है. Okay. Happy. All right. But the question is this a good running time? So what is I mean, it's not a problem really. I mean, this algorithm is all good and it's used very heavily in practice. But as far as the asymptotic nature is concerned, is this a polynomial runtime? Okay, so the answer is no, right? Remember, we talked about this kind of algorithms whose runtime depends on the numbers that are represented as part of the input. So f star is a number or whatever, this capacity of delta, whatever you want, the mean cut value. These are numbers that are part of the input, and our runtime is a polynomial in those numbers. So it's linear in such a number. So these kind of runtime are known as pseudo polynomial runtimes. So pseudo polynomial runtime. Okay. So this algorithm is not a strongly polynomial algorithm. It's a pseudo polynomial algorithm. Okay. But the good news is there are faster algorithms. So we would not be describing them in this lecture. If you take some other course like MAD or something, there we will cover faster algorithms for max flow. So one example is Edmund-Scarp or Dinich's algorithm. So this takes something like order of I think it's n square m. Okay. So this is still not great. I mean, n square m is well, it's much worse than what we get for Dijkstra or let's say Kruskal's algorithm for finding spanning trees. But flow is a more difficult problem, so we have to live with it. There are even faster algorithms. I don't want to go into them, but yeah, the point is we also have strongly polynomial algorithms. Okay, but in practice, it's often found that this simple Ford-Fulkerson implementation really gives you the best answer. Okay, great. No, I'm not saying that you have to find f star. Why are you bothered about finding f star? I mean, this is an asymptotic analysis of the performance of your algorithm. So all we are saying is that the runtime of this algorithm is bounded by the minimum cut size of your graph, and that is part of the input. So see, before running your algorithm, we never look at the graph and try to estimate what the runtime would be. I mean, that we only know after we run the algorithm. But in hindsight, this cannot exceed the value of your minimum cut, which is a property of your graph, is all I'm saying. So even if you want to think that, okay, f star is some value that we are computing that is not really part of the input, all I'm claiming is that the value of the min cut is part of your input because it's a property of your graph. Okay. Yeah. Good. All right, so let's not do anything. So next day, so a couple of lectures I will spend now on applications of max flow. Yeah, so we will see that many apparently unrelated problems can be reduced to the problem of solving maximum flows in a suitable network. So we'll talk about matching. We will talk about let's see some interesting applications. So the plan is I'll try to spend a couple of lectures on those applications, and then maybe I talk a bit about computational hardness, maybe 1 or 2 lectures, and that should be the end of the syllabus that I want to cover. Okay. So as such, today's lecture end, but now I have to address a question that was raised. So Prithviraj, your question was, in the proof of C implies B, could you repeat as to why Fe prime is equal to C prime? Okay. So are you still there? Okay. Great. So all I said was the following. So suppose this is your residual graph, right? So are you convinced that these green edges cannot appear in your residual graph? Okay. So now you know that these green edges cannot appear. Now let's look at the original graph. Okay. Now suppose this green edge is part of your original graph. ठीक है? तो ये आपका original graph में है. Now the claim is इस पे अगर कुछ residual flow बचा है, कुछ residual capacity बचा है, okay? What effect will it have on the residual graph? ये जो green edge है, this is a forward edge. Now let's say I give you a flow F and there is a residual capacity on this edge. तो जो flow F है, CE prime minus FE prime is strictly positive. So what will that imply in the residual graph? No, there is no flowing back. So remember, how do we construct the residual graph? So let's say this is a forward edge in your graph, right? UV. Okay, this is a forward edge in your graph. तो इसका capacity है CUV और इस पे flow आपका है FUV, right? Now suppose CUV minus FUV is greater than 0. Okay, तो ये आपका residual graph में क्या होगा फिर? Okay, so you have to go back to the definition of a residual graph, right? So residual graph में you will add this forward edge and उसका capacity आप कितना set करोगे? You will set this difference as the capacity. क्योंकि you also have a chance to push more flow even in the forward direction. तो ये backward edge नहीं है, ये forward edge ही है. ये भी forward edge है और इस forward edge के वजह से यहाँ पे भी एक forward edge है. And if this is not true, that this flow is exactly equal to its capacity, then कुछ बचा हुआ है capacity and ये बचा हुआ capacity मैं इस पे डाल दूंगा अभी. So you will have an edge like this which has positive capacity on in your residual graph, and this cannot happen. Okay, so that's true for the green edges in your graph G. Right, exactly. So अगर ये है तो then ये dotted green edge exist करेगा, but we just proved that that does not exist. So now we can claim the same thing about the purple edges here. So think about a purple edge here, okay? So this again is in the original graph, which is sticking back into A. I claim that the flow on this is 0. Why is this true? अगर ये flow non-zero है, तो then again, what does this imply for the residual graph? Well, अगर ये non-zero flow है, तो residual graph में I will use this edge. Yeah, that's a backward edge. और इसका capacity कितना होगा फिर? Its capacity is equal to the flow. Exactly. Its capacity is equal to the flow that is currently on E double prime. तो वो अगर positive है, तो then I will again have a green edge like this. Yes, exactly. So that's why Fe double prime has to be 0. And all this follows from the fact that the condition C is true. Okay. Any further question? Yeah, you're welcome. Why can a green not be the graph? Which green? You mean the dotted green? Aha. Okay, good. So how did we construct this cut? Remember, I am starting with the condition that there does not exist an ST path in GF with positive capacity. तो ये A और B मैंने कंस्ट्रक्ट कैसे किया? वेल, आई एम लुकिंग एट माय रेसिडुअल ग्राफ, आई एम स्टार्टिंग अ BFS और DFS search from S, and I am trying to find all the vertices that are reachable from S. That forms my set A. Okay, and all the other things form my set B. तो अगर ये डॉटेड ग्रीन एज है, ये डॉटेड ग्रीन एज अगर एग्जिस्ट करता है, then should my BFS stop at this point, or should I include some other vertex in A? What do you think? Yes. No, not necessarily to T. Okay. I am not okay. Okay. No. Okay. Not necessarily to T. So suppose this is a vertex. अब ये guaranteed नहीं है कि यहाँ से T reachable है. This is not guaranteed. I mean, I don't know whether that happens. But all I can say is that I can increase the size of my cut. Okay. My BFS, I mean, if this is V, then V should be part of A. Yes, exactly. So that is all I can say. But since that's not the case, which that means that ये green edge exist नहीं करता है. Okay, good. Further questions? Great. So then let me stop.